A variable resistor is a resistor of which the electrical resistance value can be adjusted or varied between any 2 points. Here you can see you can vary the resistance value between any 2 points. For example, this one is the variable one. You can vary the value between this or between this point and this point. So you can vary the value of the resistance between any 2 points. It can be a two-terminal device or a three-terminal device. This one is the three-terminal device. This one is also a three-terminal device, and this one is a two-terminal variable resistance device. So the two-terminal variable resistor is called rheostat, whereas a three-terminal variable resistor is called potentiometer. These are the potentiometers. The central point is normally the point at which the variable value of that resistor is measured, whereas the other two extreme terminals, like shown over here, these are the extreme terminals, are at the fixed value. These extreme terminals represent the net value of that potentiometer as well. Now coming to another component, which is the capacitor. A capacitor is a device that stores, these are the physical appearances of capacitors. Here you can see this one is an electrolyte capacitor, and these are the non-electrolyte. They can be an electrolyte, but their polarities are normally not mentioned. An electrolyte capacitor symbolic representation is like this. It has positive and negative plates. The polarity is marked on it, whereas if these are the ceramic capacitors, they have no polarity, they are non-polar. Their symbolic representation is like this. This one is polarized capacitor, which has a polarity, and these are the non-polar capacitors which have no polarity. Capacitor is a passive electronic component with two terminals. Its unit is farad. The subunits are picofarad, nanofarad, and microfarad, etc. When capacitor get fully charged, it is just like a DC battery having charge stored in it. Large value capacitors are used in battery banks for providing heavy current to a power circuit. Capacitors are used both in AC and DC circuits. The quantity of charge stored in a capacitor is termed as its capacitance, which is measured in farad. Capacitors can be of two types, fixed and variable, as shown over there. These are both fixed capacitors. I'll show you the variable capacitors. These are the variable capacitors. A fixed capacitor has two terminals, whereas a variable capacitor has three terminals. The central one is variable, like shown over here. This one is a variable. You can see by varying this terminal, you can change the capacitance between any two of the terminals. With respect to this one, you can vary the capacitance either across this terminal or across this terminal. The central one is variable, whereas the extreme ends are at fixed value. This one is the variable, and these are the fixed values. These terminals are at fixed value. This one is another important component, which is called the diode, a rectifier. We can call it a rectifier. A rectifier is a special kind of diode. This one is the symbol of diode. This is the physical appearance of diode, and this one is the symbolic representation of diode. Which converts alternating current into a DC current. And AC current is capable of reversing its polarity periodically, while direct current constantly flows in a single direction. It is also used for protecting the circuit from damaging due to the application of reverse polarity of the power supply connections. Its testing is performed on an ordinary digital multimeter. It is a passive component, its polarity is marked on it. A strip appears like the one over here. This one is a strip, round strip. It appears close to any terminal. This one is the closest terminal to this strip. Determines the negative terminal of that side. This one is the negative terminal of your rectifier. Here you can see also a strip over here. So this one is marked as negative terminal of a rectifier, and the other would be the positive terminal of the rectifier. The negative terminal is also called the cathode of the rectifier, and the positive terminal is also called the anode of the rectifier. This one is another diode which is called the light emitting diode, which is also called LED. LED emits light when an electric current passes through them. LED must be connected the correct way around. The diagram may be labeled A or positive. This one is labeled with A, or with A mean anode and positive mean the positive side of this light emitting diode. You will have to connect your voltage, the positive side of your voltage source, or the positive terminal of your voltage source, with the anode of this light emitting diode. And K or minus, this one is K stands for the cathode, and this minus sign indicates that the negative terminal of your power supply will be connected with this terminal of the light emitting diode, which is the shorter one. This one is the lengthier one, and this one is the shorter one. The cathode, this one, is the short lead, and there may be a slight flat on the body of round LEDs. LEDs can be damaged by heat when soldering, but the risk is small unless you are very slow. No special precautions are needed for soldering most LEDs. Never connect an LED directly to a battery or power supply. It will be destroyed almost instantly because too much current will pass through and burn it out. LEDs must have a resistor in series to limit the current to a safe value. For quick testing purposes, a 1 kilo ohm resistor is suitable for most LEDs if your supply voltage is 12 volt or less. Remember to connect the LED the correct way round. This means you will have to take care of the polarity of this LED, otherwise you will damage the LED. LEDs are available in red, orange, amber, yellow, green, blue and white. Blue and white LEDs are much more expensive than the other colors. The color of an LED is determined by the semiconductor material, not by the coloring of the package, the plastic body which is called the package. LEDs of all colors are available in uncolored packages, which may be diffused, milky or clear, often described as water clear. Now we will discuss about the digital multimeters, which are called DMMs. This one is a digital multimeter. These are also digital multimeters, whereas this one is an analog ampere meter. This one is the galvanometer, which is also an analog measuring uh, analog meter, which is used for measuring very low values of the currents. This one is also a shape of analog multimeter, but you will definitely widely use digital multimeters. So we will discuss upon digital multimeters. Later on, we'll discuss about some analog multimeters, but our main emphasis is on digital multimeters. Digital multimeters are designed and mass produced for electronic engineers. Even the simplest and cheapest types may include features which you are not likely to use. Digital meters give an output in numbers, usually on a liquid crystal display. The central knob has lots of positions, and you must choose which one is appropriate for the measurement you want to make. This one is the central knob, like this one. This one is the central knob. If the meter is switched to 20 volt DC, for example, then 20 volt is the maximum voltage which can be measured. This is sometimes called 20 volts FSD, full scale deflection, where FSD stands for full scale deflection. For circuits with power supplies of up to 20 volts, which includes all the circuits you are likely to build, the 20 volt DC voltage range is the most useful. DC ranges are indicated by voltage symbols representing DC values on the meter. You can take the measurements of voltages, of currents, and of resistances with the help of these digital multimeters. These are the measuring probes of digital multimeters which are being used for measurement purposes. For measuring current, your selector switch would be at appropriate current selection range, and these measuring probes, or you can bring these digital multimeters into series configuration with that circuit through which you want to measure the current. So in case of measuring voltages, you will have to connect your digital multimeter in parallel configuration, and while measuring electrical currents, you will have to connect your digital multimeter in series with the measuring terminals of your electronic circuit. What is voltage, what is current, and what is power? Current is the rate at which electric charge flows or past a point in a circuit. A circuit is an arrangement of many electrical components like wires, power supplies, switches, and different other components. Voltage is the electrical force that would drive an electric current between 2 points across which the potential difference or voltage is being introduced. Voltage is the cause, current is the effect. Voltage attempts to make a current flow, and current will flow if the circuit is complete. Voltage is sometimes described as the push or force of electricity. It isn't really a force, but this may help you to imagine what is happening. It is possible to have voltage without current, but current cannot flow without voltage. Here you can see the three circuit configurations. In this one, you have the voltage and the current. Because the circuit is in closed circuit configuration, you have connected the load in series with the power supply in this circuit. The current is flowing now. The switch is already closed, making a complete circuit so current can flow. So here, voltage and current both are present over there. Here in this circuit, you can see the switch is open. There is a voltage source, but since the switch is open, the circuit is open. No load current is flowing through this circuit. So you can say voltage is present, but there is no current. The switch is open, so the circuit is broken and current cannot flow. Here in the third configuration, no voltage and no current. You can see over there, there is no power supply connection or no DC power source over there. So when there is no DC power source or there is no electrical potential over there or the DC supply over there, so there would be no current flowing through this load. Now I'll give you a comparison between a current and a voltage. Current is the effect. It cannot flow without voltage. Voltage is the cause which produces current. Voltage can exist without current. The unit of current is called ampere, whereas the unit of voltage is called volt. Current is measured with ampere meter of digital multimeter at ampere setting, whereas the voltage is measured at voltage setting of your digital multimeter. Current creates magnetic field, voltage produces electrostatic field. Current remains same through all components connected in series with a voltage source. Voltage get divided across each component accordingly in series configuration. Current gets divided accordingly through each component when connected in parallel, whereas voltage remains same across all components connected in parallel with a voltage source. Now here you can see how voltage is being measured connecting a voltmeter in parallel. Voltage is a measure of the energy carried by the charge. We may call it energy per unit charge. Voltage is supplied by the battery or the power source. We say voltage across a component. Here you can see whenever you want to measure the voltage with the help of your digital multimeter, you will have to connect the probes of your digital multimeter across the load because you want to measure the voltage across this lamp, which is your load. So you will have to connect your digital voltmeter or your digital multimeter across this load. The probes of your digital multimeter will be connected like this one showing in this diagram. So we say voltage across a component. Voltage is measured in volts. Yes, we know it. Voltage is measured by the voltmeter connected in parallel. Yes, you have connected the voltmeter in parallel across the road. The symbol V is used for voltage in equations. Voltage is difference of electrical potential between 2 points. These are the 2 points across which you are going to measure the voltage. But in electronics, we often refer to voltage at a point, meaning the voltage difference between that point and the reference point or the 0 volts. Here, later on, I'll show it to you. These are the two circuits drawn. 0 volts could be at any point in the circuit. It is normally the negative terminal of the battery here. In this case, the 0 volt, which is your negative terminal of your DC battery. So 0 volt could be any point in the circuit. It is normally the negative terminal of the battery or the power supply. This is your power supply. This is the negative terminal of your power supply or your battery, which is also called a 0 reference voltage. Whenever you want to measure a voltage with respect to this point, which is your negative terminal of battery, you will definitely assume it to be at a 0 volt or 0 potential. Whatever you want to measure, you will have to take all voltage readings or all voltage values with respect to or with reference to this 0 value of the voltage, or with the 0 value which is your negative value of this voltage. This negative voltage value of your power supply and this imaginary 0 volt reference created by you are the same things. You will often see circuit diagram labeled with 0 volt. Yes, here you can see this is labeled with 0 volt. So we'll take all our measurements with respect to this 0 volt. So whenever you want to measure the voltage across this point or across this point with respect to this point, then you are using the reference 0 volt. In case of dual power supply, here you can see the power supply is something different. You have seen previously, here the power supply is only the plus and the minus terminals showing over here. But here you can see the power supplies, there are two power supplies. One is this one and the other is this one. This is the central point of these two power supplies. 0 volt for the circuit with a dual power supply. These are the dual power supplies which have the 0 reference, or I have shown you in a previous symbolic representation that this point represents the symbol of an earth or the 0 volt potential. Some circuits require a dual supply with 3 supply connections, as shown in the diagram. There you can have the 3 supply connections. This one is at the positive value, and this one is at the negative value. This one is at the 0 potential. This positive value is more positive with respect to this 0 volt, and this negative value of your power supply is more negative with respect to this 0 volt connection. For these circuits, the 0 volt reference point is the middle terminal between the two parts of the power supply. You can see over here, this 0 volt potential is at the middle of your both power supplies. On complex circuit diagrams using a dual supply, the earth symbol is often used to indicate a connection to 0. Yes, here you can see the earth symbol, which is a connection to 0 volt. This helps to reduce the number of wires drawn on the diagram. The diagram shows a plus minus 9 volt dual supply. The positive terminal is at positive 9 volt, the negative terminal is at minus negative 9 volt, and the middle terminal is at 0. But whenever you want to use this supply for an 18-volt potential or 18 volt as an 18-volt power source, you will have to use these 2 points. These 2 points gives you 18-volt DC. This one would be negative value of the DC voltage, and this one would be the positive value of your DC voltage. With you can, when you measure voltage across these 2 points, you will measure 18-volt DC. Now coming to another topic which is very important, the current. Current is the rate of flow of charge. We say current through a component. Yes, if you want to measure current, this is a circuit. Here you can see the load, here is the battery. If you want to measure the current through this load, you will have to insert your ampere meter in series with this load. We say current through a component. Current is measured in amps. A current is measured with an ampere meter connected in series. To connect in series, you must break the circuit and put the ampere meter across the gap as shown in the diagram. Yes, you have created the gap and you have inserted your ampere meter in series with the load of this circuit. Now you are capable of measuring the DC current flowing through the load with the help of this arrangement. The symbol I is used for current in equation. 1 ampere is quite a large current for electronics, so milliamperes are often used. Milli means thousandths part. 1 milliampere is equal to 0.001 amps, or 1000 milliamps would be equal to 1 ampere. The need to break the circuit to connect in series means that ampere meters are difficult to use on soldered circuits. Most testing in electronics is done with voltmeters, which can be easily connected without disturbing your circuits. Here one thing is very important, that the wave is moving along the time axis with the passage of time. You can see over here the wave is moving onward with the passage of time. So in alternating voltages, the wave shapes look like that they are moving from their origin towards the endpoints because of the variations. A signal is referred to a voltage of value very low. For example, a voltage level in microvolts or in millivolts are called signals. An electrical signal is a voltage or current which conveys information. Usually it means a voltage. Normally we consider the signal and measure them as voltages. An alternating current flows one way, then the other way continuously, reversing direction. An AC voltage is continuously changing between positive and negative. The rate of changing direction is called the frequency of the AC, and it is measured in hertz, which is the number of forward-backward cycles per second. Here you see the wave shapes or the waveforms of alternating signals. Here you can see a sinusoidal waveform. This waveform can be of the current or the voltage, but on measuring instruments like oscilloscopes, to see the wave shapes of these signals, we normally use voltages as a signal inputs. These are the voltage signals which are shown on an oscilloscope. The alternating voltage appears like this waveform. Similarly, we can have another wave shape which is a triangular wave. And in digital electronics, you will use many other wave shapes which we'll discuss later on. Those wave shapes are rectangular or a square wave in square wave configurations. Here in this topic, we'll discuss about AC, DC, and electrical signals, how they looks like. AC means alternating current and DC means direct current. In resistive circuits, the current and voltage are in phase, whereas in inductive and capacitive circuits, either the current will lead or the voltage will lead. Now we come across the direct current. Direct current always flow in the same direction, but it may increase and decrease. DC voltage is always positive or always negative. If it is positive, it is above the zero axis, and if it is negative, it is below the zero axis. But it may increase or decrease. Electronic circuits normally require a steady DC voltage or DC supply which is constant at one value, or a smooth DC supply which has a small variation called ripple. Cells, batteries, and regulated power supplies provide steady DC voltages, which is ideal for electronic circuits. Power supplies contain a transformer which converts the main AC supply to a safe low voltage AC. Then the AC is converted to DC by bridge rectifiers, but the output is varying DC, which is unsuitable for electronic circuits. Some power supplies include a capacitor to provide smooth DC, which is suitable for less sensitive electronic circuits. Lamps, heaters, and motors will work with any DC supply. Okay, gentlemen, we have made some arrangements for you to show the AC, DC electrical wave shapes. Now, here you can see the frequency generator. Here you will see the value of the frequency which is being generated through this generator. These are the three main functions: the sine function, the triangular function, and the square wave function. We'll later on use one by one and show you the wave shape which appears at the screen of your oscilloscope. Your oscilloscope screen will tell you how the wave shapes are being generated and how they look like. We know AC means alternating current and DC means direct current. AC and DC are also used when referring to voltages and electrical signals. This frequency generator or the function generator generates the relevant signals, the voltages, to see upon the screen of your oscilloscope. This one is the time axis, which is at the zero potential. Here I have adjusted this time axis at the very zero potential. You can see this one is the zero line, and this is your vertical line at which you will see the magnitude of the voltages appearing at this line. For AC, you will see your sine wave will definitely cover the upper part as well as the lower, because it is varying with respect to time. You will see the wave shape that the function generator will generate for you. Now here I'll generate the three functions of the wave shapes, this sine wave, the square wave, and the triangular wave. Here, I press the button to generate a sine wave. This one gives you the frequency of the sine wave. Now look at this. The sine wave appears. We can change the frequency of sine wave. You can see how the frequency varies. When the frequency varies, you can see the time period reduces. Now look at this. This is a pure sine wave. Look at another wave, which is the triangular wave. This one is the triangular wave, which is generated by the function generator. And the third one is your square wave. You can see over here the square wave. Now look at this. The square waveform is generated. You can see from here to here, then there, then here, it drops down, and then it attains the lower value, and then it again rises up, and then it attains its upper value, then it again drops down, and then it again attains the lower value, and so on. This gives you the wave shape of a square wave. You can change the frequency of the square wave. Look at this. We can change the frequency from the function generator. We can change the frequency. Look at this. By changing the frequency, you can see that the time period also changes. So this was all about the wave shapes which I have generated for you to show you a glance of this, how they looks like and how they appears at your test equipments. Later on, you will use them in different applications, and for you, I think there would be no difficulty in understanding how the sine wave looks like, how the square wave looks like, and how the triangular wave looks like. Now, I'll give you another waveform which is something like a DC waveform. You can see over here all these waves, the upper half remains above the zero voltage level, which is the time axis level, and the lower half remains below the zero axis level or the time axis level. In all the cases, you can see over here for square wave, again there is an upper half, there is a lower half. In triangular wave, again you can see there is an upper half, there is a lower half of equal amplitudes. And look at this, at the sine wave, you can see there is an upper half and there is a lower half. They are very symmetrical by all means. Now, one thing, another very important, I'll give it to you, I'll show it to you.